So now we have a way to represent this, right? Okay, so what do we do, right? Well, like I said, we're going to have to define this recursively. We're going to start with our first term, and then we're going to use this to help us with our next few terms. So, well, like I said, we're going to take the limit of our process. So I'm going to say the limit as k approaches infinity. And this is just going to be of h sub k, right? Because we're finding our kth happy number as it goes to infinity. And as it goes to infinity, if that number is equal to 1, then it's happy, right? I'm sorry, I didn't mean to call this a happy number. It's just our kth number in the process. If that equals 1, then it's happy, you know? So we're just taking the limit as k approaches infinity of h sub k, right? So the kth number in the process. So this is equal to the limit as k approaches infinity of this expression. And we're going to need a lot of space. Okay. So actually, let me write that in red. Here, it would look better in red. Okay, so here we go. So the first one, we can say for k equals 1, and we're going to use a lot of space here, so I'm going to put k equals 1 here. It's going to be equal to the concatenation from I equals 1 to n sub 1 of a sub 1 sub I. Okay, so this is our very first number, this is our starting, and from then on, so for all the k's greater than or equal to 2, we're gonna have to use some of this information, and we're gonna use a few pieces of information. So first off, we're going to start with let me just make sure I'm doing this right. Okay, so yeah, basically we're going to say this is the sum, right? And let me just make sure the indexes are all, yeah. So basically we're summing up. So yeah, because we said this is equal to h sub k, so we're going to be summing up these, right? So I'm going to write this down. Okay, so this is equal to h sub k, right? And you might be like, oh, okay, so we're done. Why did I leave this extra space here? Well, that's because we need to kind of talk about where these k minus 1s come from, because we really don't have much of a way to go from here to here. Because this a sub 1 is kind of abstract. It's like, where is this coming from? Because, like I said, like this concatenation, this, like for what we have right now, like this number can only, like the only number that can be written as a concatenation is the very first number. We don't say anything about concatenation like here, so for any number greater than 2. So we need to include that condition. So I'm going to say such that the number can be written. So basically we're going to look at h sub k minus 1, right? So we're going to look at the previous number, and I think I'm going to have enough space. We'll see. And that's just going to be, yeah. And so we know that h sub k is equal to this. So h sub k minus 1 is going to be equal to the concatenation from I equals 1 to n sub not k but k minus 1 of a sub k minus 1 sub I, right? So h sub k is equal to that, so h sub k minus 1 is equal to this, okay? And this is our expression, okay? It's crazy, right? You probably weren't expecting a really like weird formula like this, but it's how it works. So this is our first number, k equals 1, and our second, or you know, for everything greater, for every k value greater than 2, greater than or equal to 2, we have this expression, right? And we have it in terms of what we're doing and how we're getting there at h sub k minus 1. So this allows us to close the bridge between the first one and everything thereafter, okay? So I'm going to put a closing thing here. I know it's not totally proper to do that, to put a closing thing, but I just wanted to say that if this is equal to 1, right, then if and only if, it'll mean that h sub k is happy. And this may shock some people, this may be a little surprise, but I'm going to say for all k in the natural numbers. And the natural numbers, I'm going to say start at 1, 2, 3, and so on, right? I'm not including 0 as a natural number because it just doesn't help us for our case. So I'm saying that every number in our process, so for all k values, so k value will just be whatever index we have, the number will be happy. Does that make sense to you? Because we know that if 82 follows this process, we already know that 82 is happy. But what if we omitted that one and we started at 68? Well, if we go through the same process, then we'll find that 68 is happy. We also know that 100 is happy, and 1 is definitely happy, right? And if we had numbers before, right, then we would know all of those numbers are happy. So every single number in this list is happy if this limit is equal to 1. And if it's not equal to 1, then we know that none of the numbers are happy, okay? So we're almost done. We just have to include a couple more conditions. And I think I can squeeze them in down here. The first one is that h sub 1 is a natural number, again, starting at 1. Now, I'm including this because we don't really have anywhere where it says that. Technically, you could be like, oh, what if h sub 1 is a real number? No, it's natural. So I'm explicitly putting that there. And the other thing is the condition that each of these a's have to be just one digit. So, so we know that the digit, so we can use the digit counting function, right, or expression that we found in the first video. So if you're not familiar with what I'm talking about when I say digit counting expression, please look at the first video because I spend most of that video developing this. We know that the floor of the log of, I have to use two parentheses, of a sub k sub I, okay, plus 1 is equal to 1. That means each of these a's must be equal, or like they must have one digit, right? And so since we have a plus 1 and a plus 1 here, we can kind of just get rid of that and say it has to be equal to 0. Okay? And this is for all, I'm going to clean this up in a second, for all k and I in the natural numbers. So what I'm saying is that for every k value means for whatever, number in our iteration we're doing, each of these terms has to be equal to, has to have a length of 1. And also for every digit in every particular term, that length of the digit has to be, or that length of the number has to just be 1. So this is 1 digit, 1 digit, 1 digit. All of these are 1 digits, no matter which number in the iteration, no matter which digit in the number, and yeah. So let me clean this up because I know some of this is all messy, so just give me a second for that. Okay, so I just rewrote everything, so I put all the initial conditions up here, or not initial conditions, but like conditions, right? And I put everything here, and I put the implication, the conclusion, and everything. Yeah, you should be able to see all that. And so yeah, so it's a crazy expression, and this is one of those videos that it's like, I kind of just found this out, and I was like I actually saw a Vsauce video, one of those like short Vsauce 2 videos about happy numbers, and I was like, wow, wait a minute, this reminds me of concatenation. We're like separating this as a sum of that. So I was like, wow, I want to find an expression for this, and I didn't realize that it was going to be this long. And I mean, it makes sense. I really hope that I was able to convey that to you guys, but I don't even know how long this video was, so let's hope it wasn't too long. I'm sorry if it was. But yeah, thank you guys so much for watching. I'm not sure if I'll do any more concatenation videos. If I find another topic that relates to concatenation, I definitely will. But I hope you guys enjoyed, and thank you guys for watching. Bye, guys.